folks, here we go, picking up right where we left off. I want to go straight into it. We're going to pick up from this problem we just did, particle in a one-dimensional box. And we're going to expand this to 2 and more dimensions, okay? So, in other words, we're going to start making this more physically realistic. So instead of our particle that can only move left and right in our 1D, we're going to now go to 2 dimensions, okay? And we still quite don't have a full 3-dimensional situation yet. Excuse me. So in other words, in this 2-dimensional problem, right, our particle is confined to this surface, okay? So it can move, back and forth in this dimension or back and forth in this dimension. So it's still confined to this little surface, but all the same, we've added 1 more dimension to make this a little more realistic. And we'll see right away, this is where this problem is going to blow up. This is where it really, really starts to get complicated. But we can do it, okay? So let's first establish what we know. Well, we know h psi equals e psi. Great. We know here we're still talking about v equals 0, okay? So my Hamiltonian is only kinetic energy, negative h bar squared over 2m times second derivative in psi. All right. But now, look, the way that we apply this to multiple dimensions here, okay? So this was 1D Hamiltonian. This now becomes our 2D Hamiltonian, okay? Where now, instead of having d dx squared, we have partial of x squared and partial of y squared to reflect those 2 different dimensions, okay? So, and there's another thing that we can do, another important technique called the separation of variables, okay? That's how we're going to do this problem. So in the separation of variables, we impose that our wave function, right, which is now a function of x and y, okay, right? We impose that it can be written as 2 separable wave functions. So this is 2 separable wave functions. So in other words, this function x of x is a wave function that only describes psi in the x dimension. And this function y of y is a wave function that only describes psi in the y dimension. Okay? So let's set this up, all right? So what I can do now, I want to establish this as the following, and recognizing in my partial derivatives here, okay, if I take the partial of psi of xy with respect to x, okay, right, then I know that now this function y becomes a constant, so I can take that out in front, right? It doesn't depend on the derivative of x, okay? And now I only need to worry about taking the second derivative of the x function, all right? Similarly, when I take the partial of psi xy with respect to y, I know that now this x function doesn't depend on that second derivative, so I can put that in front, okay? And my derivative in psi is only dependent on y. So this is what allows me to separate these variables, okay? And so now I'm going to make a substitution up here. See where I wrote, second derivative an x of psi xy, second derivative of y and psi xy. I can now replace those with these two separable solutions, okay? And that goes as follows. So we'll say substitute, all right? And so now that's going to be negative h bar squared over 2m times, and now look, we know the second derivative in x can be written as such, the y function times the second derivative of the x function. Great. And then now plus, here is the y term, and I can write that now in terms of this separable solution, okay, partial ny squared, right? And then now, of course, that's still all going to be equal to e psi, but now instead of writing it as e psi, I'm going to write it as e times x of x times y of y, okay? And so now to solve this, the method I like to use is called divide and conquer. That's my own little established method. Divide and conquer. So how are we gonna do it? Okay, well, I'm gonna do a couple steps at once, just so you see what I'm gonna do, all right? First, I'm gonna move all of my constants over to this side, the 2mh bar squared. I'm gonna move that over, okay? And so I'm gonna write that down directly. So I'm just gonna say that that is negative 2me divided by h bar squared, okay? Now, what am I going to do? Well, if I divide both sides by x of x and y of y, okay, so I'm going to divide this thing by that, which means I'm also going to divide this whole thing by that, okay? Then here's what I get. Well, so I notice now that this, the x of x and the y of y cancels, so I'm just left with negative 2me over h bar squared. And remember, that came from just pushing these constants over to that side, okay? But now, since I divided out those functions, what I recognize here is, for this function, the y is going to cancel. And for this function, the x is going to cancel. But I have to remember, I'm dividing both terms by xy, okay? So now what I'm going to get from that is, so the y is canceled, but now I have 1 over the x function. So that's going to be 1 over x of x, okay? And that's still going to be times the second derivative in x. I still have to deal with that, okay? And now I'm going to have the same thing over here on this term, where now the x and the x cancels, but I still have the 1 over y. So now that's 1 over y of y. And of course, now the second derivative of that function in y. And that all equals negative 2me over h bar squared. Okay? So now what I can also establish is the following. I can establish that my solution here for e, my eigenvalue, it's going to be a linear sum of the two solutions in x and y, all right? And so what I can also do because of that here, okay, I can now just separate these two things. So this is where I'm going to do my separation of variables technique, okay? Because I know if I just looked at the two separated situations, I know in the two separated situations, it's negative h bar squared over 2m times my second derivative in x, which equals ex and x. So I know that I can write that if I'm assuming here from the beginning that I was able to separate my dimensions, okay? Then I know I could establish this. And I know that I can also establish the same thing for the y dimension. That equals ey y of y. And I'm also establishing that each one of these individual eigenvalues for ex or ey is a linear sum of the total solution. Okay. And what I'm gonna do, so the separation that I made here, okay, what you'll notice, what I really did, I skipped a step and I didn't describe that, okay? In assuming that these are separable, okay, if I just ignored the y term, right? Look, when I multiply through the x over to that side and then reestablish the constants, I basically just reestablish each individual dimension, okay? So this allows me to show that they can be separated based on the properties of these derivatives, okay? So in other words, it's once again, when I'm taking the derivative in x, I don't care about the derivative in y. And when I'm taking the derivative in y, I don't care about the derivative in x.